So now we continue with the topic of iterated elimination of strictly dominant strategies we discussed before, and pretty much the same thing as iterated elimination of strategies which can be never a best response. So the fact that it's the same needs a proof, which we shall do, and we will connect that to rationalizability. So that's one of the beautiful connections we are going to discover. We haven't defined rationalizability, proof that there are two definitions, which provided two definitions and having proved that they're equivalent, and seen some of the interesting properties and relationships with Nash equilibria and some examples. We're now going to go into a similar topic, but it may not seem similar at the surface. So iterated elimination of strictly dominant strategies is something we did before, but now forget that, and let's say so. Okay, let's look from a single place perspective. So not like we look at the case of a Nash equilibrium, which profiles are together stable in the sense that nobody can improve what they have if the others keep what they used to do, keep doing what they used to do. But assume that you have a player who does not know what the others do and simply looks from her single perspective what is reasonable. She can use what the others could have done and all that, what they can think, but it has to be basically without any knowledge about others. In that sense, let's look from that single place perspective, like we did in rationalizability. By the way, dominant strategies is something like that, but now we are talking about something else. At least at the first glance, it's not that. It's not dominant strategy, it's something else. What we are looking at is consider what a player surely won't play. So we spoke about rationalizability, which is a complicated, in a way, complex concept, but what the player surely won't play. Okay, if something is never best response, it's something that nobody will play, because you don't want to play something which is, let alone that it's not justified by something which can be justified and all the complications of rationalizability. But if it's never a best response, you will never play something which is never best response. It's not justified by anything. So, okay, given that, let's look what happens if we just delete those who are not never best response, and then we look in the new game who are never best response again, and so on and so forth. Because it can be that in a new game someone was a best response, but stopped being so because now the space of what others can do is narrower. So you can stop being a best response. You also can think of starting being a best response, because now someone who is a best response has been deleted, but no, because you don't delete good things here. That's the intuition, but that's just the intuition. So consider what players won't play, namely iteratedly exclude never best response. Now we show this is equivalent to rationalizability for any elimination order. So let's go formally. For any pure strategy, it's never a best response. If it's never a best response, it's not a best response to any belief of that player. So there is no belief, no probability distribution about what others do, such that it's going to be a best response. An observation, it's not rationalizable, because a necessary condition for rationalizability that it's a best response to some belief about other players. We also need other things like the support of those beliefs need to be also best responses and so on, but it's necessary. So if something is never a best response, it's never rationalized. Okay. So let us prove an interesting lemma. In a finite game, a pure strategy is never a best response if and only if it is strictly dominant. Now, one direction is trivial. So if something is not, excuse me, strictly dominant, it's never a best response, because for anything, it's strictly worse than something else. But you could think of what if something is never a best response? Well, there is something, always there is something which is better, but maybe this something which is better depends on what the others do. Well, the answer is not. It is strictly dominated. Maybe it's dominated by a combination of other things, but it's strictly dominated. So, before we prove that equivalence, we just mentioned that this implies that strict domination can be defined without defining mixed strategies, just as something which is never a best response to any belief. But belief is in a way a sneaking of probability in what we have, but you don't have to define mixed strategies here. That's what we're saying. And even if mixed strategies are not acceptable, since we know that strictly dominated strategies are never best responses, it's still justified, reasonable to delete them in that sense, because we know that it's the same as never best response. Now let's prove it's the same. It's actually not so hard, but it's not so trivial either. So consider a game, and let's Si star be a strategy. Now we define an auxiliary game. The original game is not necessarily to play, not necessarily zero sum or constant sum, no. But we define a zero sum to play game, which is going to be an auxiliary game to prove that. That's a nice trick. So define a game, G prime, on two players to play a game. Just that in this G prime, the strategy set of the first player S prime is the strategy set of player I, the player we are dealing with, whose strategies we are dealing with, besides that one, Si prime. And the strategy set of player 2 is the set of all the possible combinations of players besides I. Now define the utility of player I as what the player gets, the new utility in the game G prime, the U prime, U1 prime, of what player I gets. So UR1 prime is what player I gets, minus what player I would have got if she had played as I prime. So again, the utility of player 1 prime is what player I gets for playing. So player 1 is for player I, and the player 2 is for the rest. That's the idea of this auxiliary game. So the utility I1 prime is what player I get if she plays what they do, minus what she would have got if the rest did what they do, but if she played as I prime. And the utility of player 2 in the new game, so U2 prime, is just defined as minus U1 prime. So it's by definition zero-sum game with two players. Okay, that's something we know to say something about. And this equality, which we need, you may think about something interesting theorems about equality we proved when we studied those games, zero-sum games. So let us just recap. So the consider a game and take some strategy of player I, call it some strategy Si prime. Now we define an auxiliary game Gi prime on two players. The first player strategies are the strategies of player I besides Si prime. Si prime, not S1 prime, Si prime. Let me fix that. So it's Si prime here, and the sets of player 2 just represent all the strategies of the other players, and the utilities of players are defined as the utility of player 1 in the new game. So U1 prime is what the player 1 gets, or what she gains with respect to what she would have got if she played as I prime, and the utility of player 2 is just the complement to 0. Now we have just a sequence of so that change, yes. Now with Si prime, Si prime, Si prime. Now we have a sequence of equivalences, and that proves what we need. So now Si prime is never a best response. If you know leave, what does it mean? For any strategy that's for the other players, you can call it just for any strategy set of this player 2 in the new game, which represents the other players, there is something which is strictly better. There is some Si which is strictly better than Si prime, which is in the language of this new game means that what player I would get from playing that thing is strictly better than what she would have got if she played Si prime. So this U1 prime will be positive. That's what it means to be a never best response. There is something, for anything of what others do, there is something which is better. For nothing, it's never best response. Now, this is equivalent to saying that for any, basically what we said, but for any P2, there is something which gives us Ui prime positive. We are talking about, we started with the pure strategies in the game G prime. Now, let me just make a remark about the previous step. We spoke about any mix, so it's never best response for any mix. Actually, it means that it's never best response, of course, for any. It's equivalent to saying it's never best response for any pure thing, because if it's a best response, if it's never a best response for any pure, it's never a best response for any mix, trivially. But if it was a best response for all pure, it will also be a best response for mixed things because of the linearity. So it's the same. We just we need to move to the mixed thing because there we will use the equivalent existence of Nash equilibria, or in other words, that max min equals min max. So now let's go further. So then that for any P2 mix, there is Si in Si1 prime, such that the mixed extension utility of Si against P2 is positive, is the same as saying that for all those P2, let me just look at the maximum thing, the maximum utility of player 1, U1 prime, which we could achieve with something in Sy prime. It would be always positive for any P2. Therefore, the minimum of P2s will be positive. And again, saying that for any P2 there is something which gives something positive is the same as saying that the minimum of all the P2 of what we can get from maximizing our Si of utility 1 prime is positive. Good. That's simply another way to write it. Now it's equivalent that the mean over maximum over when we go over all the P1s, now we change. We don't go over all the Si, we go over the P1 of all the mixed strategies, and from linearity is the same. Now we use the known here in the min max and in the mixed extension of a finite zero sum game, min max equals max min. So if min max is positive and only if max min is positive. That's the core. That's what we use here. Now we translate this back to our language. So max min is positive. It means that basically there is P1 prime where the max is achieved, for example, such that the minimum of the others is positive. It means that this U1 prime will be positive for any other, for any P2. What does it mean? It means that there is P1 prime such that the You just write what u1 prime means. By definition, it's ui from this p1 prime minus ui from when player I plays si prime. It should be si prime, not s1 prime. Now I'll just change it. I'll just change that. So and that happens for all the strategies of the other player. Because P2 in S2 prime is represents all the strategies of the other player. And saying that okay, now it's Si prime. Saying that S1 is strictly, for any P1 prime, for for there is a strategy of P of player 1 which is in S1 prime, so which is not Si prime. There is a strategy of player I, of course. P1 player 1 in the new game, and confusion I and 1, but you will see why. It's still clear, I hope. There is a strategy of player 1 in the new game, or there is a strategy of player I, which is not Si, because the strategies of player 1 is exactly the strategies of player I besides Si prime. Such that for anything else you could, such that that strategy is better than Si prime, regardless what the others do. There is a strategy which is better than Si prime, regardless what the others do. It means that Si prime is strictly dominant. Okay. Yes, that's exactly what it means. Yeah. So that's what we want to prove. We started with Si prime is never best response, and by a chain of if and only ifs of equivalences, we have proved that Si prime is strictly dominant, and again should be Si prime, not S1 prime. That is a bit confusing, but it's okay. Hope it's okay. Okay, so we have proved that never being a best response is exactly the same as being strictly dominated. And now let us recall the definition of iterated elimination of dominated strategies. So iterated elimination of strictly or weakly, here we are interested in strictly, but in general it can be defined for anything, of strictly or weakly dominated strategies of a game is a shrinking sequence, so a sequence which is strictly included, every new element is strictly included in the previous one, such that for any step, all the elements which existed before and don't exist now, which existed in the previous step and don't exist now, they are strictly or weakly, depending on whether we are defining iterated elimination of strictly or weakly dominated strategies, dominated in the restricted game of in the previous stage. So at any stage, we are allowed to delete some, not necessarily all, maybe all, but some strategies which are dominated in this step. In addition, if the last state in the T is strictly or weakly dominated, then the sequence is maximal. So then we can continue. And in this lecture, it's going to be interesting what happens with maximal sequence. So that's what we assume, unless we say explicitly say otherwise in this lecture. So the strategies in the end, when we have a maximal sequence, are set to survive the iterated elimination of strictly or weakly dependent on dominated strategies if the sequence is maximal. So all the strategies which survive such a sequence, they're set to survive the iterated elimination of strictly weakly dominated strategies. Of course, is that well defined? Maybe that depends on the order. It doesn't, but we have not proved that yet. So let's see Let's see an example. So it's example exercise example 61.1 from Osborne and Rubinstein. I think it's an example. Yeah, anyway, let's see an example. So here, the bottom strategy of player 1 of the role player is strictly dominated by half of top and half of middle. And deleting that, we get a new matrix here. Here, L, player 2 of the column player, is strictly dominated by R. Pay attention, it's strictly dominated by R now. It was not strictly dominated before we deleted B. Anyway, we may delete that, or we just delete that. We are just executing the deletion of a strictly dominated. We are executing deletion of strictly dominated strategies. That's an example. So we deleted that L. We are left with 2 and 1 matrix, and now T is strictly dominated by R, by M, excuse me. And we finally obtain one. In particular, this is the only mixed Nash equilibrium of the chapter. It's just an example of iterated elimination of strictly dominated strategies. And now there is a central theorem here. In a finite game, define X to be the Cartesian product of the strategy sets of players 1 to n till n. For each player, those who survive iterated elimination of strictly dominated strategies. So define n that way, x that way, and I remind you how I define the strategies. So given some process of deleting some maximal process of deleting strictly dominated strategies, let x be those who survive. Then for any player xj, the axis of that player is exactly the set of that player's rationalizable strategies. In particular, of course, it does not depend on the exact order of deletion. Now the proof is as follows. Now it actually is two ways. So first of all, let Si of player I be rationalizable, and let's prove that it survives any iterated elimination of strictly dominant strategies. So rationalizable, according to the second definition, that Zj's be those sets which support this rationalizability. For any T in this in some iterated elimination, Zj has to be in that player's strategies of that T. Every strategy in Zj is best response to a belief on the other players in Z. And therefore it's not strictly dominated in this game, which includes the other players. So one second. So by induction, we assume that all those Z's belong to all STs for any T. And therefore, since Z belong to an ST at a certain point by induction, and every strategy in Zj is the best response to some belief on the others, which all belong there. It's not strictly dominated in this game, stage C. Therefore, those strategies keep existing in ST plus 1. So we have proved by induction that J belongs to STJ for any T, and of course for any J. And therefore, so if something is in T, no, excuse me, if something is rationalizable, then supported by the J's, then it belongs to STs for any T, and therefore it also belongs to the final set, the set of those who survive iterated elimination, Xi. Now, the other direction is that we assume that someone so we look at all those who survive iterated elimination, all those in Xj player, and show it rationalizable. So take some player J and show that every strategy in Xj is rationalizable. Now, why? No strategy in Xj is strictly dominated in the game, which we obtain at the end of those of the iterated elimination of strictly dominated strategies, because it's a maximum sequence of iterated elimination. No one is strictly dominated means that for any strategy Sj, there is some belief mu j such that Sj is the best response to the belief among Xj. Now we basically have proven everything unless it's the best response among Xj but not among all the Sj. So what if there is someone in Xj which is not the best response among Xj? But if that's the case, then there is some step where it stopped being a best response. So it was a best response among STJ, but it's not a best response in this in the new set. Now, why did it stop being a best response? Because we know that it's a best response. Yeah, it's a best response in Xj. Therefore, it has to be so. Let's look at the converse direction again. The converse direction assumes that we have this set X survived of those who survive some process of determination of strictly dominant strategies, and prove that these strategies are all rationalizable. So first, we notice that no strategy in X is strictly dominated, because that's a maximum what we could have deleted. We cannot eliminate further. So any strategy as J in X has some belief mu, which such that Sj is the best response with respect to that belief. Proof that X strictly dominated is exactly the same as not strictly dominated is exactly the same as being a best response. Now, what if it's not a best response on the original strategy set? Well, it cannot be, because if it's the best response among Xj but not among the original strategy set, then there is some point at which Sj is the best response among Stj, but it was not the best response among the St-1j at the previous step. Therefore, what does it mean? It means that why can someone stop being a best response? It's easier to become a best response when you delete others player strategies. It can be only that you stop being a best response. Excuse me. Why can someone start being a best response when you delete stuff. It can be only if you deleted a strategy which used to be a best response, but then that's contrary to the elimination of that strategy. So you could not delete the strategies which used to be a best response. Therefore, there is nobody who was a best response, was not a best response and became a best response. So being a best response in X, among those in XJ, we prove that here it implies that it was also a best response among the whole set of strategies. And then it's exactly the definition of rationalizability when those sets we're talking about are XJ. Okay, so we've proven the second direction, and now so what we say is that the fact that we prove now that for any process of iterated elimination of strictly dominant strategies which cannot be continued, those strategies who have survived this process are exactly those who are rationalizable. Therefore, the set of surviving strategies in this process is independent of the elimination order. Now, that means that in the example we saw before of finding rationalizable strategies, which are the 4 strategies, we could stop once no strategy was strictly dominated. Because what we did is that, let me go back and show you the example. What we did is that basically we stopped and we could not delete anything strictly dominated because there was no strictly dominated strategies. And then we directly showed that the remaining strategies were all rationalizable. But this proves that it's enough just to stop and we cannot delete anything when there is no more strictly dominant strategies. That was the example. So I remind you that was the example. And we deleted strictly dominant strategies till we said no strategy is strictly dominated. And then we concretely proved that by definition the rest are. But that's always the case. So and then the last remark, or not the last, but something related, is that we've proven 2 important lemmas. That in the finite game, a strategy is never a best response. By the way, we spoke about minimum and maximum, so that's why we use at least the finiteness of games. A strategy is never a best response, if and only if it is strictly dominated. And we also prove the theorem right now that in the finite game, a strategy set survive iterated elimination of strictly dominated strategies. And I mean that till the end, like we said, it means that we cannot eliminate any longer. And then it means that this is exactly the set of rationalizable strategies, all the rationalizable strategies. Now, those 2 important statements don't hold in general if the rationalizability is required to be if the rationalizability required that the beliefs be independent about the opponent action. That the beliefs will be such that the opponent's actions are believed always to be independent. That assumption would change the definition, as we saw, it changes the definition of rationalizability. And the same example, we also can show that both this lemma and the theorem don't hold. So go to the example we saw again, figure 58.1 from Osborne and Rubinstein. So consider a game with 3 players. Player 1 is the row player, player 2 is the column player, and player 3 picks the table. So each one of the first two players have 2 strategies. Player 1 has strategy up, down. Player 2 has strategies left, right. Player 3 has strategy M1, M2, M3, M4. Now in this game, the players have identical paths over 3. And here, M2 is the best response when we believe that there is coordinated belief, which assumes actually coordination. So with half probability, the players 1 and 2 play upper left, and with half probability they play down right. I'll make one word, down and right. Now with this case, M2 is a better response for player, because in M1 we get half 8, 4, M2 is 4, M3 is 4, and here 3. M2 is one of the 3 best responses. M1, M2, and M3 is all best response. M2 is the best response. Therefore, it's not strictly dominated. Now, it's the best response. It's not strictly dominated. That's a proof that means the same. Now, it already shows that the lemma 1, actually the lemma does not hold in this example, because okay. Okay, excuse me. Let me continue. So it's a better response under this belief, which assumes correlated actions, correlated strategies among the players 1 and 2. But it's not the best response under any independent mixed strategies. And it's clear that if it's independent mix, I think we may have shown this already. Intuitively speaking, it has to be 1 of 3, right? No, intuition is not now, but I think we showed this. Let me see. I think we, well, yeah, we showed that M2 is not the best response for any independent distributions of the strategies of player 1 and 2, simply by the calculations. Okay, now, so for any independent mixed strategies, it's not the best response, but it is the best response for a strategy which assumes dependency. Now, what we see is therefore that being the best response depends on whether we allow assuming dependency or not. So if we assume, if we have to, if the we require that the belief always assumes independence, it stops being being a best response for any belief which assumes independence. So but it's still, of course, never strictly dominated. So it's already not true to say that this lemma holds. Now let us show that the theorem does not hold also, and that is okay. That's simple. The theorem says that surviving iterated elimination of strictly dominant strategies is equivalent to being rationalizable. Now, of course, under the assumption that you certainly have to believe only independent actions of the other, it we show that it's not rationalizable. So we show that it's not rationalizable, but it still survives the iterated elimination of strictly dominant strategies. Because it is rationalizable according to the normal assumption, which allows independence. So we also see that the example violates the theorem. So indeed, if we assume that the belief has to assume independence on the part of between the other players, and neither the lemma nor the theorem works, generally speaking. Now, another important thing is that we just spoke about iterated elimination of strictly dominant strategies. Now, what happens if we iteratively eliminate weakly dominated strategies? We know that it does not have to preserve the set of mixed Nash equilibria, but what about the order? Does it matter? So, first, being weakly but not strictly dominant implies that we've proved. By the way, of course, we are now back, after this example, we are now back to the assumption that a belief of both others can be anything, including something dependent. So being weakly but not strictly dominated implies that since it's not strictly dominated, it's a best response to some belief. So first of all, it's the more reasons not to eliminate that, or the less reasons to eliminate that. So indeed, we don't want to eliminate weakly dominated strategies. But another thing is that the set of surviving strategies indeed generally depends on the order, as we just see in this example from Osborne and Rubinstein. So first, we can just delete the top strategy, which is dominated by weakly dominated by middle, and then strategy L is weakly dominated by R, and we arrive at this matrix. And the other order is possible. For example, the other possible order is another possible order is for the reason B, which is still weakly dominated by M, bottom, and then the reason R, which is weakly dominated now by L. So we arrive with a completely different set of strategies, different pairs and all that. So to wrap up, not only this lecture, but all the lectures from this slide set, we have done quite a lot. So let's quickly wrap up what we've done in this lecture set. So we spoke about what we already knew, had known before: strong domination, weak domination, and the properties, and something unusual, which we usually don't discuss, but still we define very weak domination. Strictly Nash equilibria, also something which we usually don't have, but we just define what it means. We also spoke about the notion of security, the max-min, which can be defined not only for two-player games with constant sum, but for any number of player games without necessarily constant sum. So the best I can guarantee if the others want to screw me over, and how this balances with the notion of stability, for example, Nash equilibrium. So that in general, it's not the same in two-player games with constant sum. It is the same. And then they spoke about the addition of weakly dominant strategies, which is not something we usually do, but it's still interesting to know what happens we've shown that it can never change the max min of the player whose weakly dominant strategies we delete, but it can actually the deletion of any strategy of a player can change, but only increase the max min of other players. But that holds for the deletion of any strategy of a player. The influence on the other maximum. Then we also shown the algorithms to find the general mixed equilibrium. So that we show that first look for the pure ones and then see what happens if you want to mix things to be optimum. And we said that the user condition that a pure strategy, a mixed strategy is the best response if and only if all the pure constituents or the strategies in the report are best responses. And that's what we use. Usually we get an equation that two equal strategies are the best, and that's when we can mix. So that's was a basically algorithm for finding mixed Nash equilibrium. And then we spoke about constant sum properties, some new properties in addition to what we had seen before, like equalizing and active strategies prove that active all this is equalizing, and also that property is useful to find the equilibrium of games. And also we found an algorithm, we shown an algorithm for finding the equilibrium of constant sum games, which is in addition to the general algorithm for any game, and that use that we can just find the max mins. When I say constant sum, I mean two-player constant. That's a class which we know many other things. Just constant sum we don't know. Actually, probably we have not proven anything which is only for which would work for constant sum, which is not two-player. When I say constant sum, unless I emphasize that it's for anything, I mean it's for two-player. Then we spoke about symmetric game. Spoke about the existence of symmetric equilibria pair, mixed equilibria. And also proved that profile not only symmetric, but any profile is an equilibrium if and only in a symmetric game. If and only any permutation of that profile is a mixed equilibrium, then we started speaking about rationalizability. So we started with what beliefs mean, and we always speak, unless said otherwise, about beliefs which allow mixing which allow dependency among other players. It does not have to be dependent, but in general it can. And rationality means being optimum with respect to beliefs, one's beliefs. And rationalizability is when the action is optimum with respect to the player's beliefs, and the player believes whatever the player believes about others has to be optimal for them with respect to their beliefs, and then it has to be optimal. Those beliefs have to may believe only stuff, only actions which are optimal for those players with respect to other beliefs, and so on. And that's the logic, and that's one of the definitions. There was another definition which we proved that it's equivalent, where simply you say that there are strategies which are just everyone is the best response with respect to belief distribution on the other strategies, which are also best responses with respect to each one is the best response with respect to some belief distribution on the other strategies and so on. And that's the definition. So we also then went to discuss what that means. What can we surely delete when we look for something which is rationalizable? So something which is never best response we surely and delete it, and we prove that never best response is equivalent to being strictly dominated. It's clear that strictly dominated is never best response, but the other direction is not clear, and we prove it's the same using this nice trick with defining an auxiliary to play a zero-sum game and using this max min equal min max theorem. This, by the way, a very famous theorem. I think it can be attributed to von Neumann. So it can be, it's very similar to LP duality too, but I mean strong LP duality too. But for us, it's just max min equal to min max. And then we prove that iterated elimination of strictly dominated strategies, or never best response strategies, because these are the same. All this, when it goes to the end, all this results in the same set as all the rationalizable strategies, and therefore is not dependent on the order of the elimination, but that's not the case for iterated elimination of weakly dominant. Well, so I think it all. Bye.